I am David Woolard, the Product Development Engineering Manager for Eaton's medium voltage switchgear product line. I am here at Eaton's Power Systems Experience Center in Warrendale, Pennsylvania. We are going to discuss the controls and safety features for gas-insulated switchgear using Eaton's Power Expert xgis gas-insulated switchgear as an example. Eaton's xgis switchgear was designed and tested to the IEC 62271 standards for high voltage switchgear and control gear, which includes gas-insulated switchgear. Many of us are already very familiar with the ANSI style metal-clad switchgear. For metal-clad switchgear, an operator must open the circuit breaker before withdrawing the breaker to the test or disconnect positions. The switchgear is interlocked such that the breaker cannot be withdrawn while it is closed. Gas-insulated switchgear comes equipped with similar interlocking features. In gas-insulated switchgear, the 3-position disconnector switch cannot be opened or grounded while the circuit breaker is closed. Let's take a look at the Power Expert xgis switchgear to see how these interlocking features work. We will demonstrate both the electrical and mechanical interlocks between the 3-position switch and the vacuum circuit breaker. We see now that the 3-position switch is in the connected position and that the circuit breaker is closed. If I try to move the switch to the open position, you can see that the switch does not operate. I will now open the circuit breaker, which allows us to operate the 3-position switch. Using the push button controls, you can see now that the 3-position switch can be moved to the open position and then to the grounded position. Now that we have reviewed the electrical interlocks, let's look at the mechanical interlocks. I will begin by closing the circuit breaker. Notice that I am able to open the control compartment door safely without being exposed to medium voltage. The control compartment contains only control voltage. Here you can see the circuit breaker is closed, and you'll notice that the interlock plunger is engaged and blocks access to the 3-position switch operator cover. This prevents manual operation of the 3-position switch. After opening the circuit breaker, the interlock plunger retracts, allowing the operator to open the 3-position switch mechanism operation cover, now allowing manual operation of the 3-position switch. In air-insulated switchgear with withdrawable circuit breakers, such as IEEE rated metal-clad switchgear, after a circuit breaker is opened, an operator may move the breaker to any of the disconnected, test, or connected positions. These operations can be performed either manually or remotely using a system such as Eaton's integral motorized remote racking system. In a similar manner, in gas-insulated switchgear, the operator can move the 3-position disconnector switch to the closed, open, or ground positions either manually or electrically. And the Power Expert xgis gas-insulated switchgear offers some additional interlocks not common in air-insulated switchgear. These 3-position switch interlocks are used for controlling and or limiting switchgear operation during normal use or during scheduled maintenance events. 2 standard features on all xgis switchgear are the switch prevent close lock and the switch prevent ground lock. xgis switchgear also offers 2 optional locks, the switch lock close lock and the switch lock ground lock. I will first demonstrate the prevent close lock. This is used to prevent anyone from closing the 3-position switch. This is an especially useful feature for spare breakers that should remain isolated or grounded while not in use, or when taking a lineup out of service. This is common in main configurations and applications with redundant lineups. The circuit breaker is currently open and the 3-position switch is closed. One very important feature of these 4 switch locks is that they cannot be applied unless the switch is in the proper position. Because the switch is currently closed, I cannot apply the prevent close lock. I must first open the 3-position switch. After the switch reaches the fully open position, the prevent close lock can then be engaged. All 4 of the switch interlocks can be locked with either a key lock, padlock, or a lock hasp, allowing multiple operators to apply their locks. After the prevent close lock is engaged, the switch cannot be closed neither electrically nor mechanically. However, you can see that the switch can in fact be moved to the ground position both mechanically and electrically. The switch is now in the ground position. I will now open the switch electrically. I must first close the 3-position switch operator flap. The prevent ground lock operates in a similar manner. I will first return the switch to the ground position. Notice that the prevent ground lock cannot be engaged while the switch is in the grounded position. I will return the switch to the open position. Now that the switch is in the open position, I will engage the prevent ground interlocks and apply a padlock. Again, all 4 of these switch interlocks have provisions for hasps or padlocks to be used in addition to the key lock system. With both the prevent close and prevent ground interlocks engaged, the 3-position switch is confined to the open position. The switch cannot be closed or grounded. When performing maintenance on medium voltage switchgear, it is critical to isolate and ground medium voltage circuits. For ANSI or IEEE metal-clad and metal-enclosed switchgear with withdrawable or draw-out circuit breakers, the circuit is isolated by opening the vacuum circuit breaker and then withdrawing the breaker to a disconnected position. Grounding of the circuit is then accomplished through the use of both manual and or electrical ground and test devices such as this ground and test device. These devices incorporate 2 sets of 3 stabs for connecting either the line or load of a medium voltage circuit to ground. For fixed mount circuit breakers, which are most common in the IEC markets, and for gas insulated switchgear, which always uses the fixed mount circuit breakers, the circuit is isolated and or grounded through the use of isolation switches and ground switches or 3-position disconnector switches. Let us discuss the lockout-tagout procedures for the xgis switchgear, which are used in potential maintenance scenarios. The breaker and 3-position switch are currently closed as they would be under normal operating conditions. To ground the cables and lock the switch in a safe position, the operator first opens the circuit breaker and then isolates the 3-position switch. The operator would then use the 3-position switch camera or the viewing port on the front of the switchgear to visually verify that the 3-position switch is in the open position. Before grounding the switch, let's look at the breaker open push button interlock. The breaker open push button interlock is used to prevent tripping of the breaker only when the 3-position switch is grounded. Note that while the switch is ungrounded, the interlock coil prevents the operator from applying the breaker open push button interlock cover. So let us move the switch to the ground position and visually verify that the 3-position switch has been grounded. Now that the operator has verified that the switch is grounded, the breaker must be closed before the breaker open push button interlock cover can be applied. After closing the breaker, which grounds the breaker cables through the 3-position switch, the breaker open push button interlock cover can be closed and locked in place. Notice there is a limit switch behind the cover that engages when the lock cover is closed. The switch disconnects the trip circuit and prevents opening of the circuit breaker electronically, while the button cover prevents mechanically opening the circuit breaker. The circuit breaker and circuit breaker cables are now locked in the grounded position. Voltage detection systems, or VDS, provide a means to reliably check the absence of voltage in switchgear. A VDS system is included as a standard feature of xgis to detect absence of voltage in the cable compartment. There are also 2 interlocks that incorporate feedback from the VDS systems, both of which are related to safety. The first interlock prevents an operator from grounding the 3-position switch when voltage is present in the cable compartment. This prevents the operator from inadvertently creating a ground fault. To demonstrate this first interlock, we will simulate medium voltage using a low voltage power supply. I will connect the red voltage lead to the VDS voltage lead. I will now connect the green voltage lead to the switchgear ground bus. I will turn on the low voltage power supply. You can see that there is no voltage at this time, and that it is confirmed by the flute meter, which is connected to the VDS system. I'll now turn on the voltage output and increase the voltage to approximately 4 volts, which will simulate medium voltage on the cable side. You can see that the voltage detection system high voltage red light is on, and at this time I cannot ground the 3-position disconnector switch. I will now turn off the voltage, and I can now ground the 3-position disconnector switch. The second prevents the closing of the circuit breaker when the 3-position switch is grounded if voltage is detected in the cable compartment. This also prevents the operator from creating a ground fault. Additionally, these control circuits are designed in a fail-safe manner such that if there is a VDS system failure, it would also prevent the operator from moving the earthing switch to the ground position or closing the already grounded circuit breaker onto the live cables. Using the same setup as the previous demonstration, we begin with the switch grounded and the breaker open. I will now turn on the low voltage power supply. I will now turn on the low voltage power. You can see that the red high voltage light turns on, designating medium voltage in the cable compartment, and that I cannot close the circuit breaker. After now removing the low voltage signal, the red light designating high voltage in the cable compartment turns off. There is now no voltage in the cable compartment, and I can close the circuit breaker. Additionally, these control circuits are designed in a fail-safe manner such that if there is a VDS system failure, it would also prevent the operator from moving the earthing switch to the ground position or closing the already grounded circuit breaker onto the live cables. In summary, prior to operating any gas-insulated switchgear, it is critically important to understand the available controls and safety features that are offered, including interlocking of the isolating and grounding operations. The Eaton Power Xpert xgis gas-insulated switchgear product was designed with a strong focus on the safety features to ensure operator safety, from the medium voltage utility and substation to the downstream feeder breakers. If you would like to learn more about Eaton's Power Xpert xgis gas-insulated switchgear and see a live demonstration, please contact us or your local Eaton representative to schedule a visit to Eaton's Power Systems Experience Center.